actually an interesting subject because it gets at the physics and chemistry that operate when particles start to approach surfaces, and how do you predict what will happen in terms of their transport? And my focus is on groundwater, on understanding how far colloidal materials, and when I say colloidal materials, I mean nano and microparticles of all different kinds. So when I say colloids, I'm using that as a term to lump together all sorts of different types of materials that range in size from nano to micro. And I'll talk more about that in just a bit. But I'm going to focus on the fact that when we try to predict transport of how far these things will go, for example, in groundwater, in a granular, say, sand aquifer or gravel aquifer, it's very difficult to make that prediction because under environmental conditions, there is repulsion between these colloids and the grain surfaces. And it usually arises from there being like charged. And we call that condition unfavorable conditions for attachment. Because they, in the environment, tend to be both negatively charged, that creates a repulsion that makes attachment unfavorable, and it's very difficult to make predictions, as I'm going to show. So what I'm going to talk about is the fact that you need nanoscale heterogeneity to explain colloid attachment to grain surfaces under environmental conditions, but that also extends to many, many other contexts, including transport and biological systems, including transport and engineered systems, wherein you have repulsion between the particles or the colloids and the surfaces. And so what we do is implement something we call discrete representative nanoscale heterogeneity into simulations. And what we find is when we do that, we can capture the sensitivities to solution ionic strength and to the size of the colloid. And so we can predict things like detachment in response to reduce solution ionic strength, and I'll talk about why that's important in a bit. We can show that there's a reason why we have reduced attachment for colloids that fall in this so-called nano to micro transition size range, from about 200 nanometers to about 2 microns. And we can also show how we can begin to predict these so-called non-exponential distributions from the source that I'll talk about in some detail. And this is work, of course, I didn't do by myself. This is all my students, most recently Cesar Ron, Anna Farnsworth, and Kurt Van Ness. And it was all funded by the US National Science Foundation, a couple different programs, hydrologic sciences and material sciences. So what I'm going to talk about is recently written up. I wrote this in a book, a textbook. And the important thing I was trying to achieve with this textbook, and it was written by me, but also Eddie Pazmiño made some contributions to the text and to the figures. And so we're co-authoring this text. And we're trying to explain processes across multiple scales, from the nano to the pore to the continuum scale. And so it's a free textbook through the Groundwater Project. If anybody's interested in a copy of that textbook, just email me at the address below, william.johnson@utah.edu, and I'll get you on the list for a free copy. But the idea is for this textbook to explain the underlying principles, but to also allow people to work out their own simulations and realizations using freeware that we have distributed that's called Party Suite. And I'll talk about that in a little bit too. So here's an illustration by Eddie regarding colloid transport in groundwater. It's a ripoff of a famous ES&T image, but we use in the textbook, so we had to draft our own. And what it shows is colloids can be, these green colloids represented here, look like bacteria, but you can also think of them as clays or other colloids, and they can carry contaminants. They can be contaminants themselves in the case of pathogens, or they can carry contaminants like radionuclides. And that's the point, that we care about colloids because they can be contaminants or they can carry contaminants. And so we need to understand them. We also need, most importantly, to understand their transport. And that's well demonstrated by this example from the Washington County Fair in 1999. This comes from Steve Prudy at the University of Alberta. And in this incident, several thousand people became ill Some of them from E. coli 0157H7, some from Campylobacter, and some from other pathogens. 71 of them were hospitalized, and 2 died among the oldest and youngest of the population. And there was a shallow well from which drinking water was supplied to this event. It was only 7 meters below the ground surface, and it was located only 11 meters from a septic tank seepage field. And that well had undergone quarterly microbiological monitoring for 4 years and had only shown 1 detection in a different well of E. coli. There was no evidence of potential for contamination. And yet after the outbreak, they performed a dye test. And that showed that when they added dye to the toilet in the nearby latrine, that dye appeared in less than 10 hours in the supply well. And of course, 10 hours is far less than pathogen inactivation rates, which take on the order of months. And so it showed that there was a strong transport connection that had not been realized. And so it's clear that we can't just rely on monitoring, we need to understand transport potential. And that is part of what motivates my interest in being able to predict transport distances. Now, one thing I want to say about particle transport or colloid transport is that in the interaction with surfaces, specifically grain surfaces in a granular aquifer, the process is not straining, because straining is the entrapment in pore throats too small to pass. And straining, when it occurs, leaves a cake on the media or in the media where the pore throats become too small, and that will clog the granular media. So what we're really talking about is filtration, where the colloids are much smaller than the pore throat or the pore body. And so they find their way to surfaces through diffusion and then attachment. They aren't strained. And of course, filtration rather than straining really has to be the main operating process, because our groundwater is generally higher water quality relative to our surface water. So it has to be able to transmit the groundwater while capturing the particles. And so filtration is the process I'll focus on here. So the way that particles move through the subsurface is influenced by different forces. And so on the bottom right here, one primary force is the diffusion force, which randomly moves the particle in 3 dimensions. But in addition to the diffusion force, there's a fluid drag force from the flowing water, there's a gravity force from the density of the colloid, and there's a colloidal force that I'll talk about in some detail. But just focusing on the diffusion force for a minute, it's worth considering the scales across which we're operating here. So at the lowest end of the scale, 1/10 of a nanometer or 1 angstrom, you have molecules. And molecules can range up to the size of around 1 nanometer. Your proteins, your very complex molecules, are in that size range of 1 nanometers. Beyond that, we talk about nanoparticles. Those are the smallest colloids. 1,000 times larger than that is the micron size range, and that's the size range of bacteria. And then in the 10 micron size range, that corresponds to protozoa and other large colloids. So that span from the smallest colloids to the largest colloids is 4 orders of magnitude, a factor of 10,000. Now, to really understand the significance of that, think about common scales that we work with, say 10 centimeters to 10 meters. People would consider that a vast change in scale, but that's only 2 orders of magnitude. So when you think about the fact that colloids range over 4 orders of magnitude, it makes one realize, oh, there could be many, many differences between the smallest colloids and the largest colloids. And one of the primary differences is diffusion. And that difference is even bigger for solutes in this angstrom to nanometer range relative to colloids in general. So the solutes in the smallest colloids have very high diffusion. They can, in the pore space, diffuse so rapidly that they find surfaces. They can almost be guaranteed to find surfaces. Whereas in contrast, larger colloids have very low diffusion, they aren't guaranteed to find surfaces, and so they will only reach surfaces if they're on fluid streamlines that impinge on surfaces. So there's very important differences between these behaviors across this size range. And just to say, one important contrast here is that solutes can undergo reversible interaction with surfaces because of their high diffusion. Colloids don't tend to undergo reversible interaction with surfaces because of their low diffusion. And so that's an important contrast to keep in mind. So the forces that occur when colloids approach surfaces come from three important origins. One is van der Waals forces that operate out to distances beyond about a couple hundred nanometers. Beyond that, they're insignificant. And so those van der Waals forces are the farthest reaching interactions. Whereas when colloids approach surfaces to closer separation distances, say within 100 nanometers or several tens of nanometers, the counterions that shield the charge on the colloid and the surface of the grain surface get squeezed. There's an electroosmotic repulsion. In this schematic, both surfaces are assumed to be negative. So what's being squeezed between them are their counterions that are cations. And so that electroosmotic repulsion increases as the particle moves towards that surface. And then if the particle can get close enough to the surface such that it's actually touching, the electron orbitals overlap, and that brings a very strong repulsion into play called Born repulsion. It's physical touching. And so you superimpose those forces and you get this feature. It's non-monotonic. And the point being that there's an attraction, a weak attraction out in the 100 nanometer separation distance range. There's a repulsive barrier from the like charges, the counterions being squeezed between the surfaces in intermediate distances. And then there's a very strong attraction at very close separation distances around 1 to a few nanometers from the surface. And so increased ionic strength, where you increase the counterions between the surfaces, decreases that repulsive barrier and changes this profile. But the shape of the overall profile is known by a primary minimum at very close separation distances, that's attractive, a repulsive barrier at intermediate separation distances, and then a weak attractive zone called the secondary minimum at still greater distances than the repulsive barrier. Now, this is all for what we call unfavorable conditions. The two surfaces are like charged. In the environment, they tend to be both negatively charged, but the same would be true for two positively charged surfaces in, say, a biological system. So one thing that I need to be very clear about is that when we measure the properties of surfaces in many different types of experiments, we calculate the repulsive barrier based on those measurements. Basically, they're called the zeta potentials of the surfaces. And the repulsive barrier almost always comes out to be so large that no attachment can occur. And this is important because we know attachment occurs. We see it in experiments, and yet we cannot explain it when we calculate these repulsive barriers. And that's what my talk is going to focus on, is how do we explain the attachment that we do see. Now, before I get into that, though, I should also mention the scale at which most experiments are done, which is at the column scale. So this is an image of a packed sediment column. A colloid suspension is being injected into the base of the column, and fluid is moving upwards and exiting the column. And so we monitor the transport of the colloids that are being introduced using two forms of data. The top form here, shown here, is a breakthrough elution curve. So we monitor what comes out of the column across time. So initially, nothing is coming out. But if we start injecting colloids into the system, there'll be a lag that is representing the pore space, the pore fluid being displaced. And eventually, as that is fully displaced, colloid breakthrough will occur. And a steady state plateau will exist for as long as you inject the colloids. At least this is true under favorable conditions where the surfaces are oppositely charged. If there's no attachment at all, of course, they will break through to whatever concentration you're injecting, which we call C naught. And when you stop injecting, the colloids will elute and the concentration coming out of the column will go back to zero. If you then take the column and dissect it to figure out the concentrations as a function of distance from the injection side of the column, from the source, you can plot the relative concentration, the concentration that you measure on the sediment relative to the C naught, take the log of that, and you'll see that it decreases log linearly with distance from the source under favorable conditions. And this is all well described by the advection dispersion equation, where we have a transient term, an advection term, dispersion term, and a filtration term. And if we assume steady state conditions, the transient term and the dispersion term both drop out, so we can equate the advection term and the filtration term, and those together say that that natural log of the relative concentration is going to change linearly with distance L, and that slope of that log linear decrease with distance from source is equal to the filtration rate constant over the velocity. That's the average pore water velocity. So we have a mathematical construct that describes all this. This is what we see under favorable conditions. Under unfavorable conditions, where the surfaces are like charged, and again, in the environment, they tend to be both negatively charged, things get much more complicated. We can have, instead of a steady state plateau, we can have blocking where the attachment of colloids prevents a further attachment of additional colloids. And so the steady state plateau, in fact, rises as you inject the colloids. Or the attached colloids actually attract more colloids to the sediment surface, and that's a process called ripening. And the steady state plateau is not constant, it actually decreases as you inject more. But in all cases, once you stop injecting, instead of the concentration decreasing to zero, you get what's called extended tailing. There's slow re-entrainment of colloids back into the bulk fluid that keep showing up in the breakthrough curve. And so there's more action happening relative to favorable conditions. And if you dissect the column, it's never log linear. Instead, it is multi-exponential. So a log linear curve is exponential. The curve we always get in terms of the profile of retained concentration is not exponential. It's in fact describable by considering the population to have both sticky and non-sticky or unsticky colloids, so that the sticky ones get retained a gradient of the non-sticky colloids. And we see this at all scales, not just the column scale. We see this in the field. We did work in a gravel channel at Notre Dame University, and these are the breakthrough elution curves. But the point is we can back out the filtration rate coefficient describing the breakthrough at each location for 4 different colloid sizes, ranging from 60 nanometers up to 7.7 micron in diameter. And all of them showed this decreasing filtration as a function of transport distance, consistent with this idea that the population is getting less sticky as it moves forward, as it transports down gradient. That's a major problem for prediction. How do we predict how far things will get if the population is effectively changing while it moves? And this, of course, applies to pathogens, it applies to clays, it applies to nano and microplastics. All of these things show this behavior. So at the pore scale, what's happening is shown here. On the left side is the favorable conditions. These are 2 micron colloids and 550 micron diameter grains. And in the left, in the favorable conditions, when the colloid gets to the surface, it just sticks. There's no action at the surface. Whereas on the right, under unfavorable conditions, you can see that many colloids get near the surface and then slowly translate along that surface. And some of them actually find places to attach, and some of them get swept into the rear flow stagnation zone. So there's a very apparent difference between favorable and unfavorable conditions at both the pore scale and at the column scale and at the field scale. So that motivates us to understand how to link in our predictions the nanoscale interactions, this repulsive barrier, that drives these pore scale and column scale and larger scale differences. And we use different collectors to represent this in numerical simulations. A very popular one here is the Happel-Spherin cell, where you have a fluid envelope surrounding a spherical grain. It's a very idealized version of an aquifer grain, but it is effective. And so I'll talk about that as also this Hemispherian cell where the grain-to-grain contact is explicitly represented. But these are the collectors we do simulations in. And so we can capture the behaviors we saw under the microscope. On the left side is favorable conditions in a force and torque balance, accounting for all the forces. And you can see that they turn magenta, which is corresponding to the secondary minima, but only for a short time. They snap into contact and attach very quickly on the favorable side. On the unfavorable side, we have to add small zones of attraction, so-called heterodomains, to allow these colloids to attach. Otherwise, they would all just move along the grain and eventually exit. But when we have these heterodomains here, the colloids can roll into contact with heterodomains and the attraction can become dominant, and then they can attach. And you can see that this colloid is rolling over some heterodomains, but they're not occupying enough of its interaction with the surface to allow it to attach. And perhaps as it rolls to the other side of the grain, it will find those heterodomains and attach. But that's the difference between favorable and unfavorable. We can capture those dynamics in these simulations. Great, but how does this relate back to reality? Well, remember that if we run simulations with no heterodomains on an unfavorable surface, no attachment occurs, as shown on the left. They simply all move along the grain surface and then exit, those that get to the grain surface. Whereas on the right is shown a simulation where we add nanoscale heterogeneity and then we can allow attachment. So we have to figure out what size even corresponds to reality. What are the characteristics of nanoscale heterogeneity that represent the surfaces that we're working with? And so the problem we run into is that whatever technique you use, spectroscopic or spectrometric, you will detect heterogeneity. That's just the way analyses are. The question is, what scale and surface coverage of heterogeneity that you detect is even relevant to your colloid transport? And so I like to say that the resolution or that what you detect depends on the resolution of the analysis or the brush that we use to paint the surface. And so what we have to do is work at this from both sides, from an experimental side and from a theoretical side using simulations. And so we use the simulations to try to back out what are the scales and surface coverages of these heterodomains that are relevant to the colloids that we're studying. And so we can get at this by the fact that the surface that is seen, that is the heterogeneity that is seen by the colloid, depends on its size. And that's shown here in this image. These are three different size colloids, and what's shown in the red, yellow, and blue are the zones of interaction. That is, when a colloid is interacting with a surface, and just assume this red disk is part of a larger surface the colloid is interacting with, there's a finite zone across which the interactions are significant. The curvature of the colloid is such that other parts of the colloid are too far away from the surface to have significant interaction. And so that zone of interaction is proportional to the colloid size. So that the largest colloid has the largest zone of interaction, the smallest colloid has the smallest zone of interaction. And let's suppose there's heterogeneity on the surface, shown by that green disk. Well, you can see that the heterogeneity occupies a small fraction of the zone of interaction for the largest colloid. And so the interactions will be predominantly repulsive with some attraction in the very center of that zone, but not enough to remove the barrier. So you get this red, large repulsive barrier. In contrast, the smallest colloid, the heterodomain occupies a majority of the zone of interaction and the barrier can be eliminated. So what the surface looks like to a colloid depends on the size of the colloid. Likewise, the ionic strength affects the zone of interaction. Not only does the size of the colloid drive the zone of interaction, but also the ionic strength through the Debye length. And so at low ionic strengths, the zone of action is quite large, or the zone of interaction is quite large. Whereas at higher ionic strengths, the zone of interaction shrinks because the Debye length is shorter. And so for a given size colloid, at low ionic strength, it may experience a repulsive interaction because the heterodomain occupies a small fraction of the zone. Whereas at higher ionic strength, the heterodomain may occupy a much larger fraction of the zone of interaction, and that may flip the interaction from repulsive to attractive. So both the colloid size and the ionic strength drive these interactions. Likewise, and I should mention, so storms and disease outbreaks are correlated, well correlated. It's been well described in the literature. One mechanism that can help drive this correlation is the fact that when you have heavy rainfall, you decrease the ionic strength of the solution. So you're running the system this way. You're expanding the zone of interaction, meaning a heterodomain that may have attached a colloid under previous conditions may cause it to detach under low ionic strength conditions, and so detachment would occur. We've shown this in a number of papers. And so that's one mechanism driving that, potentially driving that correlation. The other attribute that drives the way colloids interact with these heterodomains on surfaces is diffusion. And so we can look at 3 different colloid sizes. We have a 100 nanometer colloid size in blue, which I like to call the mosquito. And in these trajectory simulations, what it does is it diffuses back and forth at a range of distances from the surface, from 30 microns down to just a few nanometers. And because there are repulsive conditions, it cannot attach, but it diffuses back and forth over a large vertical distance. In contrast, you take a much larger colloid, a 6.8 micron colloid, and that's shown in green. That one has much lower diffusion, thousands of times lower diffusion. So when it comes into proximity with a surface, it does not diffuse back and forth across large range of separation distances. And in fact, it basically sniffs along the surface like a bloodhound because it has low diffusion and it has a very strong secondary minimum. So it has strong van der Waals attraction holding it in association with the surface as it translates along that surface. And then you take an intermediate size, like a 1 micron colloid shown in red. I call it the hummingbird because it's transitional between the mosquito and the bloodhound. Okay, it shows some behavior of both of those, but there's a whole continuum. And the reason this is important is that it affects the likelihood that the colloid will be able to find those heterodomains. There has to be enough diffusion or fluid drag to push it or either allow it to diffuse across the surface in order to find heterodomains on the surface. So finally, we can have heterodomains not just on the collector, but also on the colloid. We can track whether or not the projections of those interactions are constructive, additive, or whether they're destructive, overlap, and actually cancel one another. So we have all this in our simulations in this freeware we call Party Suite. And what we do is we run arrays of experiments of different colloid sizes, as shown in the x-axis of these plots, different pHs, 6.7 in the top row, 8 in the bottom row, and different ionic strengths, 20 millimolar on the left, 6 millimolar on the right. And with all that data, we can then try to back out what is the heterodomain size range on the collector and the colloid that explain all these experiments. And what we find is we can explain it. That's what these lines are. They're simulations, and they assume power law distributed heterodomains ranging in size from 25 nanometer to 90 nanometer in radius. Okay, so we can back out attributes of these surfaces using that approach. Okay, that's great, but that alone isn't very convincing that we're doing something useful. But what convinces me that we're doing something useful is that we can start to look then at the pore scale simulations on those surfaces to understand how long did it take these colloids to attach. And what we see is that the reason we have this minimum, this very low minimum in the nano to micro size range transition, is that those colloids take longer to find heterodomains and attach. Their residence times in the near surface or in the bulk fluid plus near surface are much longer than the other size colloids. And that's because they have the lowest combined fluid drag and diffusion. And that inhibits their ability to find these heterodomains. So we're starting to be able to explain experimental data based on fundamental processes. And we can do more with these resonance times. And the way I'm going to introduce that is to first talk about how do we move from the pore scale to the column scale and beyond, first under favorable conditions. And that's shown here where we look at the porous media as a series of grains. In this case, series of hemispheres and cells. And the point being that we can idealize the process of moving through a porous media as such. And we can say that if the concentration coming into the porous media is C0, that a fraction, so-called eta, of the population is lost to the grain surface. That's what eta is. That's the so-called collector efficiency. It's the fraction that attach relative to the fraction that enter. And then what exits is 1 minus eta. So C1 over C0 is 1 minus eta. And that's true for every grain in the series, so that by the time you get to the nth grain, the ratio of Cn over C0 is equal to 1 minus eta to the power of the number of the grains or collectors passed. And we can do a log transformation of that and equate that to the simplified equation I introduced to describe column experiments based on the rate coefficient. And that allows us to predict the column scale rate coefficient from the pore scale eta. That's how we do this upscaling to understand these processes. And so we can make a prediction based on, we can make simulations at the pore scale to get eta, and then we can make a prediction of column scale transport by the KF that we calculate. And so we can do that quite well when we run experiments. The blue curves in favorable are predicted quite well from the etas that we simulate at the pore scale. And that's what people have been doing for decades now. The first people to do this were people like Charlie O'Melia and Chi Tien and their students working in the 70s. And that was established, long time ago. But what has been the challenge is explaining all these red behaviors, these unfavorable condition behaviors. And so that's where I want to go next. I want to talk about the fact that we can take these pore scale simulations and we can look at these resonance times in terms of histograms. And so what's shown here is simulations in the top globe that are under unfavorable conditions versus simulations in the bottom globe under favorable conditions. And what we see is under unfavorable conditions, the colloids get to the near surface and repulsion keeps them from attaching, so they move along the near surface for very long resonance times. And it shows in the histograms. Under favorable conditions, all attachment occurs within about 10 seconds of resonance time in the near surface, or within about 100 seconds total resonance time in the entire collector. Whereas under unfavorable conditions, the near surface resonance times are much larger than those under favorable conditions. And the total resonance times before attachment are much larger than most of those under favorable conditions, but there's overlap. We can call this overlapping section the fast attachers, call them alpha 1. Those are ones that attach relatively fast under unfavorable conditions at timescales that match favorable conditions. Whereas the remainder we can call alpha 2, the slow attachers. Their resonance times before attachment are much larger than those observed under unfavorable conditions. And we can take those two populations and make predictions, okay? And I probably should do this slide first. I have these out of order. Let me go forward. The way we do that is expand this analysis that I showed you above. Instead of just talking about things getting to the grain surface, we can talk about the colloids getting to the near surface environment, where the repulsive barrier takes over and delays their attachment. And so applying that same process I showed you above for favorable conditions that results in this equation, we can apply it to unfavorable conditions to say there's also a slower attaching fraction to get this relationship between eta and a slower attachment rate coefficient. And that's, I won't go into the details in implicit versus explicit But what I will talk about is the fact that we can reconfigure these rate coefficients. And so going back to this slide, what I want to show you is that we can take the fast and the slow attaching populations and have two rate coefficients associated with them that were developed, the equations for which were developed by kind of expanding our upscaling that was traditionally used for favorable conditions and expanding it to unfavorable conditions. And when we do that, we find that we can predict a fast attaching fraction and a slow attaching fraction that together give us this non or multi-exponential profile of retained colloids. But to get that, what we have to do is make an unconventional assumption. And we have to assign what happens to colloids that don't attach, but just end up at the rear flow stagnation zone of the grain. We do that with a knob that we turn called the alpha RFSZ and the alpha trans. What that's doing, that knob, alpha trans, is saying what fraction of those colloids that get to the rear flow stagnation zone move to the near surface of down gradient grains. So that's a knob we're twisting. Okay. The other assumption we have to make is that those fast attaching colloids are not replenished, and that's an unconventional assumption. But we make it on the basis that pore scale mixing is not complete. You don't have complete mixing in the pore scale, and in fact, you may not replenish certain fractions of colloids. And so this is demonstrated in work by Deanna and others in two-dimensional porous media where a fluorescent tracer is invading from the left and moving to the right. And what you see is, and I should say the high concentrations of the tracer in black, low concentrations of the tracer in the white or cream. And you can see that there are zones of incomplete mixing where the fluorescent tracer does not go, at least not immediately. Those areas fill in as diffusion allows, but you can see the streamlines very quickly. And these zones of incomplete mixing propagate from rear flow stagnation zones to forward flow stagnation zones of down gradient grains. And those are important locales for colloid delivery and colloid accumulation. So it's not surprising at all that there might be a relationship, or it's quite possible that there's a relationship between these zones of incomplete mixing and the lack of replenishing or the depletion of certain fractions of the colloid population. So that's an assumption that we have to start to prove using pore scale modeling, but pore network modeling. So, but when we make that assumption, we can actually obtain the curves that are observed under unfavorable conditions. And I just want to say that you can do this in Party Suite. That's available to you. It's at this website here, shown at the bottom, wpjohnsongroup.utah.edu. And we're happy to help anybody that wants to do either the nanoscale interactions, the pore scale trajectory simulations, or these continuum scale simulations based on the pore scale. Contact us if you're interested. But I can show you its application in a particular context. This is the Central Sands of Wisconsin, where we were looking at reasons for why there are lower pathogen detections in these sands relative to other parts of Wisconsin. And the hypothesis is that they undergo greater filtration. But we wanted to do transport experiments and see if we could actually characterize them based on the nanoscale interactions. So we looked at 3 colloid sizes, 100 nanometer colloids, 1 micron colloids, and 4.2 micron colloids, all carboxylate modified latex microspheres. And so we did these packed column experiments, and what we saw is your typical breakthrough curves for the 0.1 micron or the 100 nanometer. You see in the red here, there's a breakthrough plateau and then tailing that is almost as high as the plateau. For the 1 micron, you see a plateau, and then there's also tailing, but it's lower than the plateau. And then the 4.2 micron, you seem to see some blocking, but when you stop injecting, you see some tailing as well. And the resulting profiles for these 3 sizes are shown below. And what you see is that they're all multi-exponential. They're not log linear. The log linear relationship predicted from filtration theory, just based on the physics of things, is shown in dashed lines. And you can see that they hugely underpredict the transport of these things. That predicts that they would all be captured in the first increment of the column. But instead, they're spread all along the column. They got much farther than predicted by filtration theory. So what we can do is use what's called an alpha to fake it. We can force the breakthrough to not be as low as predicted by filtration theory, as shown by the dashed lines in the breakthrough curves, and instead just force it to match the observed breakthrough plateau. And when we do that, the profiles then look more like the data in these dotted lines. But you can see, for example, in the dotted line for the 4.2 micron colloids, there's a huge amount of mass that's predicted to be at the upgradient end of the column that in fact isn't there. They moved much farther down gradient than predicted by even that forcing an alpha to improve the prediction. So we instead turn to this idea of a fast attaching and slow attaching population, running pore scale simulations to look at those two populations and their residence times before attachment in those simulations. We had to assume a certain surface coverage by heterodomains. To do this, I won't go into detail on that, but that's the only assumption we had to make. And then we could look at what these residence time distributions would predict in terms of the distributions at larger scale. And so when we did that, we ended up with these matches to the breakthrough curve. They're not perfect by any means, but they're much better than either of the conventional approaches give. And what's also quite nice is that the distributions with distance along down gradient in the column do a much better job. The simulations do a much better job describing the experimental observations than we see by the conventional approaches. So I'd consider that a success. It only involves assuming a surface coverage by heterodomains and then making the assumption that, or using the knob that decides what fraction of near surface colloids that end up in the rear flow stagnation zones also will be transmitted to the near surface of down gradient grains. But having two knobs to turn and to get this kind of complexity, I think is a good improvement. And really what we're doing is we're linking the nanoscale interactions to the column scale transport, which to me is a useful process. So what I've done is shown that nanoscale heterogeneity drives colloid attachment under unfavorable conditions. I've shown that implementing the discrete representative nanoscale heterogeneity produces new sensitivities to solution ionic strength and captures detachment in response to reduced solution ionic strength. I didn't actually show you that, but I can. We have papers published on that. Shows you that the reduced attachment for nano to micro transition colloids is explained. And we can produce these non or multi-exponential colloid distributions from the source. So with that, I'd be happy to answer any questions you might have.
Thanks, Professor Johnston. Very informative presentation. So, any questions? Otherwise, you can just, okay, also you can write, just type in the chatting board. That's fine. Yeah, I think Professor Wei Zhang, he wants to ask some question.
Thanks, Wei.
Thanks, Bill. Thanks, Chen. Bill, that's a great presentation. I really enjoyed it. And I have a comment, rather a question, but maybe I start with a comment and then follow up with a question. I remember when I was in grad school and I first heard your talk in the AGU meeting. I think it's Fort Lauderdale in Florida. And in that meeting, you presented about your simulation work. I was really amazed by that. And it was great to follow your work over the years and to see the progress. And seems you are now, I would say maybe you have solved the colloidal transport mystery in the groundwater. That's great, and it's also great that you did this textbook project, so people can kind of learn what you have learned and apply what you have learned to their own work. So that's great. And so my question is, now you have solved the colloidal transport mystery in the groundwater. Do you think like what you learn can be applied to the unsaturated soil, in which you have the air, water, and a solid phase, and those are constantly changing. So the pore structure in the presence of air phase is changing constantly. Is there a way to kind of address that challenge?
Yeah, no, it's a great question, right? Because it's always the case, the more you know, the less you know, right? Because the fact is that we're addressing a very idealized representation of transport and granular media. So I'm only talking about saturated conditions and everything I've talked about so far. And I will answer your question, but one thing I want to say is it's very generous of you to say we've solved it, because we haven't really. What we have done is shown that you can use nanoscale charge heterogeneity to explain attachment, and in fact, explain a lot more, right? We've shown that. Is that, though, the actual cause of everything we see? Probably not, because we explicitly represented nanoscale charge heterogeneity. We didn't explicitly represent roughness, which can also create a variety of outcomes. People need to do that, and we'll start working on it. But other people who may be working on roughness, I would love to help you be the ones to incorporate that, to show, oh, okay, actually part of this is explained by roughness, for example. Okay, now to get to your question, yeah, I haven't even touched on saturated conditions, right? But you could in fact even take these idealized models and introduce an air-water interface. Now, at the simplest would be a static air-water interface. So you're not looking at capillary interactions, you're only looking at the DLVO interactions, the colloid surface interactions, but now with an air-water interface, right? That would be the simplest way to incorporate unsaturated conditions. And that could be done, and we've thought about doing that, particularly in the hemisphere cell model, because in that model, you could create a pendant of fluid that would actually be a fluid-air boundary. And we just haven't done it. I mean, there's, how it is. You get started on something and it always takes you much more time than you ever think. And so we just never have gotten around to it. But I would love to work with people who are working in unsaturated conditions to actually incorporate air-water interfaces into these pore scale models to see what can be gleaned. Because the trajectory analysis is very powerful. The force and torque balance is very powerful, and applying it in a system with an air-water interface would, I'm sure, produce really interesting results. And then, how do you get to a dynamic air-water interface? Well, that's got to be at the pore network, pore network level. And I can't even begin to start addressing that right now. We're barely addressing the pore network level under saturated conditions right now. So I could say stuff, but it would just be a bunch of baloney. So I won't. But hopefully that partly answers your question.
I think you're modest, because I think even though you said you address a small part of the problem, I think it has been shown to be very powerful. Like I have seen in the past in your presentation about how you actually apply in the real world, right? Like a riverbank filtration, and
Right.
you presented one example, like the gold mine work you did delivery in South America. So that was amazing work. It's kind of outreach and engagement, and actually working on the environmental system. So that's great. Hopefully, we can kind of see more of your work in the future.
Thank you. Right.
Hello, Bill. So I may ask question. So since my group is not get too much about the modeling, so for the colloid, but we do some colloid interactions with contaminants. So is that a way, because sometimes we are also interested to do some modeling, such as because the colloid can be a carrier for the
Right.
For example, something like So in your model, so what kind of you need to add some interactions with contaminants, and also some for the modeling. So can you just give some brief explanation? Thank you.
Yeah, and that's actually where I started. My PhD was in facilitated transport of organic compounds by a dissolved natural organic matter, which you can think of as a colloid, right? It's a large molecule, but they get into the colloidal size range. And so my simulations on that focused on partition constants between contaminants and colloids, between colloids and surfaces, and between contaminants and surfaces, right? So you have these three equilibria that are being satisfied during transport. And you're right, the colloid can be a facilitator of the transport. The colloid can be an anchor, right? If the colloid actually has a greater interaction with the surface, then it can actually slow the contaminant down. And you see all of these different things depending on the contaminant, depending on the colloid, and depending on the grain surfaces. So those kinds of simulations exist, and they tend to be described by equilibrium partition constants. But as I've said, that for the colloids, equilibrium partition constants don't actually apply. It's not an equilibrium process. And so we could make those models more sophisticated by using a filtration rate coefficient for the colloid, but retain an equilibrium partition constant between the contaminant and the colloid, if that's appropriate, and between the contaminant and the surface as well. And you can get into all the things about, well, is it a linear relationship or a nonlinear relationship? But those are all addressable, right? So these multi-component models, yeah, they exist, and we've done it. And it's a somewhat different type of simulation than what I've been showing here, because these simulations are focused solely on understanding the colloid transport. But it's not a difficult step once you've got that to then add in contaminant interaction with the colloids and contaminant interaction with the surfaces themselves, right? And that's something I'd be happy to talk more about, because I know I'm kind of simplifying it, but the fact is that in some ways the contaminant interactions are a little easier because we get to them empirically. They're a little easier to get at empirically. And so we can actually insert these partition constants, or whether they're nonlinear or linear, people typically get them from batch experiments. And in fact, you have to get them from batch experiments because you don't have this deterministic element that you have with colloids. That's what makes colloids so interesting. Their diffusion constants are relatively low, so you can model their likelihood of getting to surfaces and predict what the filtration rate constant will be. Whereas for solutes, their diffusion is so high, you can almost be assured they'll get to the surface. But then the question is, how strong is their affinity for the surface? And that's very hard to get at with the simulations, but you can get at readily with batch experiments. So I don't know if that answers your question, but those are my thoughts.
Thank you. Yeah, thank you very much. It's very complicated. Yeah.
Yeah.
Mm-hmm.
And like I said, I really encourage people who are interested in trying to bring simulations to bear on either colloids or solutes and colloids. I'd love to talk to people to help them move this forward, because we have this resource. The textbook was written to actually help people utilize this freeware. If you're interested at all, ping me, because I will send the textbook once it's approved.
Yeah. Thank you. Yeah, I definitely do that. Thank you.
Well, I appreciate the time.
So
Bill,
you have another question? Yeah.
Yeah, before you go, I don't know whether we have other question from audience, but I do have one, because your last comment kind of intrigued me. So my students is currently doing some simulation of amino acid with a graphene surface. So she's using molecular dynamics. She's able to track the movement of the individual amino acid molecule. So they move, like they jump around and moving back and forth. So it's kind of like it's exactly what you just explained. So how exactly this high diffusion influence their attachment. Well, we call absorption, whatever you call it. It's the association with this entity. It could be either molecule or colloids with a surface, right?
Right. Yeah, and so the diffusion, right? Once this, let's take the amino acid. Once it associates with the surface, it may or may not stay there because this intrinsic energy that it has, all these things, colloids, solutes, they have the same intrinsic energy, which is 1.5 kT in 3 dimensions, or half kT in any dimension. But the point is that the translation associated with that intrinsic energy is much larger for a solute than it is for a colloid. Okay, that's the diffusion, right? The visible impact of that intrinsic energy. And so a solute can break free from the attractions it experiences near a surface because its translation is much larger, and relatively speaking. And so the solutes are always, that's why you establish equilibria. They're always breaking free, reassociating, breaking free, reassociating. And so you end up with an equilibrium where the mass transfer in both dimensions, in both directions, is equivalent, right? That's the definition of a partition constant. And you don't get that with colloids. Colloids, they get to the surface, their diffusion is too low to break off. They just sit there in the primary minimum. You can knock them off. You can perturb it, right? Through change in ionic strength or change in pH or a drastic change in flow rate. But without that perturbation, you don't get this equilibrium. It's a fully non-equilibrium process. And so I find that really interesting because equilibrium processes slow the breakthrough, right? You have a retardation factor associated with the equilibrium constant. They retard the breakthrough. But the breakthrough eventually comes out to equal what you're injecting. In contrast, colloids, you don't slow the breakthrough, but you reduce it. They start coming out in one pore volume, but a small fraction of them are coming out.
Yeah.
And so it's a very nice contrast between these solute-based equilibrium processes versus these colloid-based irreversible processes. And so then when you have the two interacting with one another, as you were saying, Chung, that's a very complicated system to model mechanistically, right? And that's why we tend to rely on batch experiments to get at the solute piece of it. So I don't know if I answered your question, Wei, but I've been very interested in molecular dynamics because you've got to focus a lot of computer power on just understanding a favorable configuration of molecules on surfaces, right? So what I don't know is if people doing molecular dynamics have done what we do, where you consider a whole grain surface and start to understand how to upscale to a partition constant. I don't know if people do that or not.
Yes, that is actually our ultimate goal. So hopefully we may actually arrange a meeting with you to talk about this, because our goal is to first start with amino acid, and then you hopefully we can kind of go further to the peptide fragments, and then to a protein. So like you, and then see once you do that, see if you can upscale. Even upscale the amino acid interaction with graphene cell, with carbon cell, would be very interesting because it has some applications. Yeah.
No,
Thank you so much, Bill. Yeah, it was a great elegant explanation you just did on the equilibrium non-equilibrium interaction of a solid and colloid. So thank you so much.
Yeah, thank you, Bill. Yeah, I think it's time to to close probably today's presentation, and also thanks again. So after the pandemic, COVID-19 pandemic, maybe I can invite you to Nanjing University, China, so to have more like collaboration in the future too. Thank you very much. Thank you for your support to EEH. All right.
Well, thanks for the opportunity.
Bye-bye.
Bye-bye.
Sure. Thank you. Bye-bye. Bye.